Hello everyone, it's Flight Insight Private Pilot Ground School Class 11, Navigation Planning. We covered all the basics of the different ways that we can use navigation to get around in our airplane, and now we're going to get into the nitty-gritty of how we actually incorporate this into planning a flight route out. So we're going to start using the basic parts of the plan components for the flight between College Park and Hagerstown. So we're going to start working on some of the ways that we're going to calculate those flight routes out. So let's start by looking at some of the tools that we're going to use to help us with this. This gadget is called the E6-B flight computer. It's been in use basically almost as long as aviation has been around, and it's been used by pilots to compute speeds, heading distances, different types of rates that we're going to use when we plan out our navigation. Now it looks old school and it looks like a little outdated, but if you're familiar with slide rules or anything like that, it's the same concept. So we're going to use a slide ruled side for a lot of the relationships between speed conversions and distance conversions, and then we're going to use the other side of this to compute things like wind correction and ground speeds. So the E6-B comes in a lot of different forms. The one that I like is the one pictured here. It's from King Schools, and it's because it combines the calculator with the plotter. So you just need one tool to be able to do all your tasks for it. So that's the one that I usually like to pick up, the one pictured here. Hey, look at that. Anytime somebody comes up to you and mentions that the E6-B that you have is not cool, just remember that some of the most famous aviators in the world, fictional and non-fictional, have used the E6-B when it really comes down to it. So here's Mr. Spock from Star Trek pulling out his green-colored E6-B to match the color of his blood, I think, to compute something. I think there was some crisis on Star Trek. The Enterprise was in a decaying orbit, and the captain came out and said, "Hey, how long do we have before the Enterprise is going to burn up?" And Mr. Spock said, "Oh, 1 minute, Captain." Pulled out his E6-B and came out with the answer. So obviously, anytime you have any kind of an issue with computations or anything like that, it was designed to be something that you could use in the cockpit. Are you going to use it in the cockpit every time? Well, that's really up to you, but that's the design of this thing. It's supposed to be a real at-a-glance tool, but we're going to use it on the ground to help us compute these flights. This next tool is the cross-country navigation log. It's what we're going to use to write down and record all of the planned information that we come up with at the flight, and it's one of the files that's included along with this course for you to start getting your cross countries planned out. Now, there's a lot of acronyms and abbreviations across the top there, so let's have a look at what each one of those means. So first of all, it's having you put down checkpoints. These are the points along your route of flight that are going to allow you to conduct the pilotage portion of the navigation. And then it's going to have you list out altitudes that you want to fly at. If you're using VORs, you'll use a VOR to determine a course along which you're going to fly your route, and then you'll also select a OBS heading so that you know how to fly along a given radial. You're going to put the wind direction and velocity in that next column, and it's going to be winds aloft. So it's important what altitude you find those winds at, because we're going to use those to determine our ground speed and our wind correction angle. In order to do that, we're going to need to know our true airspeed, so that'll go in the TAS column. And then we'll start to calculate our compass heading. And we're going to start with the true course, which is just the course on that sectional chart. We're going to apply the wind correction angle to the true course to get our true heading, TH, which we'll apply the magnetic variation to get our magnetic heading, MH. And then we're going to apply the deviation effect to get finally our compass heading. This is the direction that we're actually going to steer the compass in flight. We'll have determined the leg distance, the distance between each leg of our route, and then we'll know our ground speed. Both our estimated and our actual will go in there, as well as the estimated time en route and actual time en route, plus the estimated time of arrival and the actual time of arrival. The difference between ETE and ETA is, let's say we've estimated our time to be 10 minutes. We'll put 10 minutes in the ETE, but then we might put something like 1 p.m. and then 1:10 p.m. in the ETA. So that's the difference between those two things. So this is the cross-country NavLog that we'll work with. It's unclear if Mr. Spock used the cross-country NavLog while he was on the USS Enterprise, though. So to begin our flight planning, we're going to start by drawing a line to connect the two airports that we're traveling between. So we'll connect a nice line. You can draw this with a pen or a pencil, ideally a pencil so it erases, on your sectional chart. You'll use the straight edge of your E6-B or your plotter to draw this line out between College Park and Hagerstown. Now, in a real cross-country flight plan process, we would want to determine the suitability of this route, and we'll do that in the actual class where we do this flight plan between College Park and Hagerstown. But let's go ahead and assume that we've already determined that this straight line distance is going to be suitable for our flight route. So we'll use that. Now the first step here is that we're going to want to compute the distance between these 2 points. We're just going to do this as one big leg. We're not going to worry about like intermediate checkpoints or anything like that. Let's just see how far it is between Hagerstown and College Park. So we'll use that mileage scale on the side of the E6-B. Now you have to be careful which scale you use. You have to make sure that you're using the sectional chart scale for nautical miles, because a lot of the E6-Bs that you use, and again, not all of these are going to be the same, but a lot of these E6-Bs are going to have multiple scales on them that are used for multiple charts. You have your sectional chart scale, you have your terminal area chart scale, and then your world aeronautical chart scale. So make sure you're using the right one. If you're ever not sure, match it up with the hash marks on the lines of longitude, and that will, if the scale that you're using has 1 mile, match one hash mark on there, you'll know you're using the right scale. But basically on a sectional chart like we have here, you're going to want that 1 to 500,000 scale there that we're using. So here what we've done is we've overlaid that scale. We started it out there at Hagerstown, and it doesn't stretch all the way to College Park, so we'll have to kind of draw a hash intermediately at say 40 miles there, and then we can carry it on to see what the total distance is going to be. So there, if I kind of match up the 0 with the 40-mile hash I drew and then see what the rest of it is, you notice that the 40 plus 18 is going to give me my total distance for this leg of 58 miles. And next we want to use the plotter to determine the true course. If your plotter is on the E6-B, great, use that like I've done here, or if you have a individual plotter, use that too. Now the way you use this plotter is you're going to line up that center hole over the course that you drew where it intersects a straight line, either a line of longitude or a line of latitude. So notice what I've done to the center of that plotter. I've put that center hole right at the intersection between that line of longitude there and the course line that I drew. And you can even make sure it matches further by making sure that that line of longitude runs through the 0-degree line on the plotter there like I've done. And now you can read the true course off the plotter. So notice that the course that I've drawn is running through about 320 degrees. So that right there is going to give me my true course for the flight. And what we can do is we can start writing these into our NavLog. So true course is going to go in that upper box in that column there that corresponds to TC, and then the leg distance is going to go in as 58. Notice what I did on the left too. I've got my 2 checkpoints in there. I've got KCGS for College Park and KHGR for Hagerstown. And notice the orientation of the boxes here, right? That leg where I wrote the true course and the distance, that doesn't match up with one of those checkpoints. It kind of straddles the two, and that's because this leg applies to the leg between College Park and Hagerstown. So that's what the purpose of those little black arrows is for too. We can enter the wind direction and velocity into that wind column now. And again, we want to do winds aloft. So we'll have already figured out the altitude, and we'll find the altitude from that, or we'll find the winds aloft at that altitude from the winds aloft forecast on aviationweather.gov like we did in the weather information class. So let's just throw some numbers out here. And by the way, I know we're glossing over this and it seems like this might be a little bit out of order, but don't worry one little bit if you don't understand everything here, because when we do our cross-country flight between College Park and Hagerstown in class 13, we're going to do every single step here from soup to nuts. So we're not going to make any assumptions and we're not going to take any shortcuts. But here, for demonstration purposes, we're going to keep it somewhat short and sweet. Anyways, here's the wind direction and velocity. 300 degrees at 10 knots. So we're going to want that so that we can start computing ground speed and wind correction angles. Now, in order to determine our true airspeed, we're going to have to start with what we know inside the cockpit. So let's say we know that when we're up at altitude, the aircraft is going to be doing a certain speed indicated on the airspeed indicator. Now, we can know that just from experience, or we could know it from looking at the performance tables in Section 5 of the POH. What we're looking at here is also in Section 5 of the POH, and it's a calibration page that basically, if you take a certain indicated airspeed, what the airspeed indicator is actually telling you, you need to be aware that that needs to be calibrated for like errors in the altimeter or the pitot-static system. Basically, the slower you get, the more these errors start to manifest because of uneven pressure differentials in the pitot or the side of the aircraft or things like that. So what the POH has done is they've said that for a certain indicated airspeed, you have a calibrated airspeed due to these errors of something else. So at 100 knots indicated airspeed, which is what we're interested in here, you would expect to see a calibrated airspeed of 98 knots. The first calculation we're going to do using the E6-B is going to be to find our true airspeed. Now, if you have your E6-B with you, you can follow along with this. If you don't, you can do what I'm doing here, which is use an online version of it. This is the University of North Dakota. Their wonderful aerospace program has a online E6-B, and rather than just feeding it raw data, you can actually spin the wheel around and use it the way you would if you had it in your hand. So thanks to the UND for this one. So this is the slide rule side of the E6-B. What we want to do is we want to take our calibrated airspeed, which we found out to be 98 before from looking at the POH, and we want to figure out what our true airspeed is. Remember from our performance course that we talked about the difference between what the airspeed indicator says you're doing and what you're actually doing through the air. Remember, as the air gets thinner, as you get up higher or the temperature gets hotter, the amount of air molecules that the instrumentation system is playing with will reduce. So that's going to cause you to need to fly a faster true airspeed in order to get the same indicated airspeed on the airspeed indicator. So what we can do is, if we know what the outside air temperature is and we know what the pressure altitude is, we can put that into the E6-B and it's going to tell us what our true airspeed is. So in the example, we're going to use a pressure altitude of 3,000 feet, and we're going to use an outside air temperature of -4 degrees Celsius. So do you see the window here where it says pressure altitude and then the arrow is pointing over here for thousands of feet? So what we want to do is we want to spin the card around in such a way to line up the -4 degrees Celsius with 3,000 feet. You have to be kind of careful when you're doing with the mouse because, you know, one little pixel can throw you off by a fair amount. So there we are. Here's 1, 2, 3,000 feet right here, and it's lined up just on the inside of -5 degrees. So it's basically where the -4 degrees Celsius is that would impact the 3,000 foot pressure altitude. And now look at the instruction, airspeed correction. We've already done this. Set pressure altitude opposite degrees Celsius in the window. Now, opposite calibrated airspeed on the inner scale, that's this one here. Read true airspeed on the outer scale. So here's my inner scale, and I know that I had 98 knots, which is right there, for calibrated airspeed, and that's going to line up with 100 knots to give me my true airspeed of 100 knots. Incidentally, you can also read the density altitude off the center if you like. So that's going to tell you your density altitude at that temperature and pressure altitude is 1,000 feet. But what I'm here for is my true airspeed of 100 knots. So here now we'll input the true airspeed of 100 knots into that true airspeed column. So now we've got all the ingredients that we need to start figuring out where to actually point this aircraft. We've got the wind direction and velocity, the airspeed, and the true course. That's all we'll need to start figuring out our heading for computing where to actually point this aircraft in flight. So how are we going to figure out the ground speed and the wind correction angle? So back on the E6-B, instead of using the slide rule side that we used before for the true airspeed, we're going to flip it around and use the wind side. So conveniently, they've got the instructions written up top here, so we don't have to remember this every single time we do it. We can just start working one by one. Now, the first thing I do when I use the E6-B here is I like to set it to a nice easy reference. So what I'm going to do, and this does kind of make it inconvenient to read the instructions, we're going to have to kind of keep going back and forth, but I'm going to slide this guy. You see that little center hole right there? I'm going to slide that guy so that it's right underneath the 100. Just a nice easy reference. It's almost like a 0 point for the whole thing. Now let's start moving up and we'll have a look at these instructions. So the first instruction is to set the wind direction under the true index. Here's the true index, so it wants us to set wind direction. The wind direction we said was going to be 300, so let's turn this ring and set 300 under the true index. Step 2 tells us to mark the wind velocity up from the center point. This again is why I like to use 100 for my center point. Just makes things easier. So if that's 0 and the wind velocity is 10, then I'm going to put a little marker. And if you've got this in real life, you can use a pen just to mark on it. It's like a little transparency that helps you see that. But if I click there, you see a little red dot to help mark it. There we are. That's my wind speed. So that was step 2. Step 3 is now to twist this ring again to set the true course under the true index. The true course we determined was 320 degrees. So I'm going to move this ring to the left to put 320 under the true index. Notice what happened to that red dot. It moved over a little now. So let's go keep looking at the instructions. Now it says, step 4, slide wind velocity mark to true airspeed. So that mark I made, I now want to slide that to the true airspeed. And here's how I do that. So there's the mark there. I want to put it on my true airspeed. My true airspeed is 100, and that's going to be this arc right here. I basically want to slide this whole thing down until that red dot is lying right on top of that 100 knots arc, as it is right there. That's step 4. Step 5 is going to say to read the ground speed under that center hole. So now that I've slid that down, I can read my ground speed right there. That's about 90 knots or maybe 91 knots right under the center. So I know my ground speed, and then additionally what I can do is step 6, wind correction angle reads between the center line and the wind velocity mark. So basically, if it's to the left or to the right of the center line, you know it's going to be a left or right wind correction. So here's the center line, and then there's that red dot. Let me see if I can zoom in on this so that we all don't strain our eyeballs. That's a little better. So let me come out just a bit for reference. So here we are at the center line, and here's 10 degrees left and 10 degrees right. Well, this red dot is on basically what would be about the 2 degree line. So here's 2, 4, 6, 8, 10 for reference. So basically our wind correction angle is going to need to be a negative 2 degrees or a 2 degrees to the left. How do I know it's negative? Because if you want to go to the left in terms of these degrees, you go from like 320 to 318. So it's going to be negative 2 degrees of application of wind correction in order to get from our true course to our true heading. Now let's put those two figures that we computed from the E6-B into the NavLog. So we figured a wind correction angle of negative 2 degrees. That's going to go in that spot right there, the wind correction angle box, and we'll apply that negative 2. We'll basically subtract it from the true course to get our true heading of 318 degrees. And we can also park that ground speed figure, 91 knots, into that ground speed estimated box there a little bit more on the right. So now we can apply the magnetic variation. We have our true heading. We need to get to our magnetic heading. The difference is going to be a result of the magnetic variation in the area. So remember that we can figure out what the magnetic variation for our area is off of the sectional chart. We'll use that isogonic line that runs along the sectional chart in the area, and it's highlighted there in the slide just to the east of our route of flight near Baltimore. That's that dashed line, and it says 11 degrees west on it. So we'll apply that 11 degrees to our true heading in order to get our magnetic heading. Remember, if it's 11 west, we need to add it to the true course. If it were east, we would subtract it. Sometimes people use a east is least, west is best way to remember that. So like, east is subtract, west is add, east is least, west is best. I'm from the east, so I don't know that really makes much sense to me. If I were from California, I would definitely be on board with that little memory aid, but it does help a lot of people to remember, do you need to add or subtract? Well, 11 west, we're going to add that to the true course to come up with the magnetic, we're going to add that to the true heading to come up with the magnetic heading. So here that is applied here. I've put plus 11 in the variation box there, and I'm going to add 11 to 318 to get my magnetic heading of 329. The final step in this process is going to be to apply what's called the magnetic deviation to our magnetic heading in order to get our final compass heading. What deviation is it's basically acknowledging that you've got the compass in the aircraft, which is just a little magnet that's pointing towards the magnetic north field of the Earth. But there's also other magnetic fields in the aircraft. You've got a lot of electronic communication and navigation on board. All those things throw off a little electromagnetic field. It's the reason why the compass is kind of dangling by itself away from the other instruments. It's to minimize the effect of those other magnetic fields on the working of the magnetic compass, but it is still going to be affected a little bit by that. So what compasses have is they have this deviation card. So you see it there at the bottom left that it says that for any specific heading that you want to fly, you need to actually steer this heading. So let's see, if the heading that we want is 329, it's roughly 330. What it says on the compass card there is that for a heading of 330, you're going to need to steer a heading of 332. So that's a deviation of about 2 degrees. We're going to need to add 2 degrees to our magnetic heading. So we'll put that in the deviation box, and then we'll apply it. We'll add the 2 degrees to 329 to get our compass heading of 331. Now this is big and in bold because this is what we're actually going to use in flight. So I'm going to have this NavLog with me when I fly around, and I want to use this and I want to look at this and see that that's that big bold number. That's what I've actually computed out to be what I'm going to try to have my compass show as I'm flying between these 2 points. Finally, we want to figure out how long it's going to take us to get between those 2 points. So we're going to go back to the slide rule side, and this time we're going to try to compute our estimated time en route. So there's kind of a nice little short way of figuring this out, that basically you have the time in minutes on the inside scale and you've got the miles on the outside scale. So the really fast way to do this is, you see this 60 number here, it's in a box and it says rate and it's got an arrow on it, and basically what that wants you to do is that wants you to use that figure as your rate. So you said if you go a certain speed, if you go a certain number of knots, that means that you're going to go a certain number of nautical miles per hour or per 60 minutes. So there's our 60 minutes. So we computed our ground speed as 91 knots. So if I move this inner ring to set up the rate arrow on the 91 knot figure, this basically means that in 60 minutes I go 91 knots. And now I'm curious how long it's going to take me to go the 58 miles that I computed. So we'll go along the outer edge here. Here's 60, here's 59, here's 58, and you see that it matches up with about, was that 37 or 30, actually it's 38 minutes. You see that there? This would be 39. So 38 minutes is how long I'm going to use for my estimated time en route calculation. We can now put that 38-minute estimate into our estimated time en route box. Now in flight, what we can do is we can actually time how long it takes us to get between these 2 points and then put that in the AT, the actual time en route below that. What we could also do is put an estimated time of arrival. So you see up there above this, it says time off. You could write down the actual time of day that you take off and then update your estimated time of arrival based on that. So 1 p.m., 2 p.m., etc. So now we've got the full route planned out here. The only things that we've left off were the altitude and the VORs, because we'll kind of pick those up when we do the full flight plan. But really what we were interested in was figuring out how to compute our compass heading and our estimated times en route. Now we can also figure out our fuel burn for the flight. So remember that the Section 5 of the POH is going to have a performance chart in it that's going to help us figure out what our fuel consumption rate is going to be for the flight. So just to throw a number out here, here we are at 8,000 feet of pressure altitude at 2,400 RPM on a above standard temperature day, and that's where I've circled the 6.7 gallons per hour burn rate for this pressure, altitude, and power setting. So we'll know in 60 minutes how much fuel we'll burn. We want to figure out how much fuel we're going to burn in the 38 minutes that we're actually going to fly. Again, we'll use that slide rule side of the E6-B to figure this out. And 6.7 gallons per hour, that's a rate, so we're going to use that rate arrow once again. So we'll find where 6.7 is. Now notice it doesn't really go in single digits, right? It only goes 50, 55, 60. We can use it as 60, or we can use it as 6. So we can kind of choose which order of numbers we're using here. So if we're looking for 6.7, we can consider this to be 6 and that to be 7. And what that means is that each one of these is 0.1. So 6.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7 is going to be right here. So I want to align my rate arrow with that 6.7. So if I bring that right, and again, I got to be careful with the pixel here and make sure I nail it. Or maybe I don't need to be too much of a perfectionist here, right? Anyways, so there's 6.7 right there. Now what I want to do is I want to move over and see if I burn 6.7 gallons in 60 minutes, how much do I burn in 38 minutes? I'm going to have to scroll down a little bit. So here's 40 minutes, 39 minutes, 38 minutes, and you see right there that it's going to be just shy of what would be the 4.5 gallon figure. So that's 4.5, that's 4.4. That's about 4.3 gallons that I'm going to burn. We can also use the E6-B to make some basic conversions for distance, weight, volume calculations. So notice that if you line up those arrows, you notice the arrow that says naut or nautical. If I line that up with a certain nautical mileage, like 43.5 from the Interscale, and then I read the arrow that says stat or statute for statute miles, I can kind of convert my 43.5 nautical miles to 50 statute miles. And I could do the same thing for something like volume and weight. So if I know I'm taking 84 gallons, I'll put that 84 on the US gallons arrow over there on the right there. You see that? And then if I read all the way on the left where the fuel pounds intersects the Interscale, I can say that the weight of that 84 gallons is going to be 504 pounds.